Hi and welcome. My name is Mikke Tavast. I'm a PhD student at Aalto University and I'm presenting our paper titled Evaluating Large Language Models in Generating Synthetic HCI Research Data, a case study, co-authored with Perttu Hämäläinen and Anton Kunnari. Our work stems from the observation that much of HCI research is conducted using verbal or textual data. And given the recent success of large language models, LLMs, in this work we sought to evaluate LLMs as a synthetic data source for HCI research. And there could be a number of benefits of synthetic data, for example in initial pilot testing, setting up analysis pipelines and generating new research ideas. And from a broader perspective, we argue that with LLMs, computational user modeling could be expanded to new avenues, such as to user motivation and emotion. In this work, we use OpenAI's GPT-3 model to generate synthetic data and compare this to real research data from a study by Bob and colleagues concerning art experiences in video games. And we chose this dataset for two reasons. First, experiencing art is a topic that should be challenging from an AI user modeling perspective, and also the dataset is recent enough for it not to be included in the training set of the original GPT-3 models. And we conducted 3 experiments, but on this presentation I'm gonna focus only on the experiments 1 and 3. Here you can see GPT-3 in action. So I have given it a prompt and GPT-3 then continues the text by continuously predicting the next token in the sequence. Here you can see different prompts used in the experiments. So each prompt ends with a question that is directly adapted from the open questions in the Bob et colleague study. And this allows meaningful comparisons to be made between the real and synthetic datasets. So the first question asked to remember an instance where a digital game was experienced as art. The second, what is the title of the game? And third, why the participant considered this experience as art. The first experiment is a quantitative study on how distinguishable GPT-3 responses are from real human responses. And in this experiment we used the answers to the first question in the previous slide. So for this experiment we recruited participants from Prolific, and the task for the participants was relatively simple, shown here on the right side of the screen. So they were asked to read a text and then decide whether they thought it was written by a human or generated by an AI. And before the experiment, the participants had been informed that half of the text passages they will see were written by humans and half generated by an AI system called GPT-3, but that the presentation order is randomized. With methods from signal detection theory, we analyzed whether the participants were more likely to identify human written text correctly or to answer that GPT-3 generated texts were written by humans. And the results show that actually in this experiment, GPT-3 responses were significantly more often evaluated as human written than human written texts. On the figure on the right, you can see the average proportion of written by human participant answers for each stimulus in the experiment. Then let's move to experiment 3, where we investigate the content similarities between the generated synthetic data and the human data of Bob and colleagues. So the main motivation behind this study is that for synthetic data to be useful, it needs not to be only superficially human-like, but also reflect real properties of user behavior and experiences. For this experiment, we generate responses to all these 3 prompts shown earlier, although in this presentation I will mainly focus on the prompt 3, what exactly made you consider this experience as art. And we analyzed these responses using automatic qualitative coding. So what do I mean by that? The automatic qualitative coding approach combines GPT-3 powered coding of the responses and topic modeling methods. So first, we use GPT-3 to generate codes that summarize the content of the answers. And the motivation behind this coding is that it distills the essence of the answers and reduces noise. So concretely, the automatic coding is achieved with a prompt designed to guide GPT-3 to generate summarizing codes for the answers. So here you can see one answer being coded. So the few short examples in the prompt guides GPT-3 to generate codes, memorable experience, emotional response, graphics, music, and strategy, summarizing the content of the response. Once we have extracted the codes, the next 3 steps are similar to the Perttu topic modeling approach. So first, the codes are transformed to vector representations using text embedding models. The dimensionality of the embeddings is reduced using UMAP, and then they are clustered using HTTP scan. And at the end of this process, we have combined similar codes into larger groups or topics. And by counting the frequency of the clustered code groups, this allows us to compare the relevance of topics between the human and GPT-3 data. And as a side note, we are planning in near future to release a dedicated Python package implementing this approach. So if you're interested, follow Perttu's GitHub profile to keep you updated. And to the results. So this figure is a bit complicated, but let's go through step by step. So on the left, there are the human data groups or code clusters, and on the right are the GPT-3 code clusters. And they are sorted from top, from the most frequent, to bottom, to the least frequent code groups. And the lines connect each human data code group to the most similar code group in the GPT-3 data. And if we zoom on the top of the figure, we can see the most common code groups in both datasets. So for example, the most frequent group in both datasets relate to aspects of story and storytelling. The second most frequent to aspects of music and soundtrack. The third most common code group in the human data relates to experiences of beauty, and similar kind of code group can be found as the fourth most common in the GPT-3 data. So there seems to be, at least for the most frequent code groups, quite a lot of similarities. And here's another set of results from the experiment. I'm not going to go into details here, but I will just highlight that we also looked at the performance of different GPT-3 models, and we analyzed the performance in terms of similarity of the distribution of the embedding vectors for synthetic and real data. And generally the quality increased as the model size increased, but curiously the newer text DaVinci 2 model that is fine-tuned using human feedback had high quality data, but it covered less of the distribution of the real human data compared to the older DaVinci model, the original 175 billion parameter GPT-3 model. So this suggests that the fine-tuning has increased the quality of the answers but reduced the diversity of the responses. And to conclude, we find these results promising and intriguing. We feel that synthetic data could be useful in exploring possible research ideas or hypotheses, especially if combined with automatic data analysis similar to our experiment 3. That said, as LLMs are well known to hallucinate facts and generate false information, to state the obvious, confirming hypotheses on what people really think, feel, or need should be only based on real data. And unfortunately, quality requirements for synthetic data might be lower for misuse than for actual research. One possible implication of our results is that if malicious users start using LLMs in online crowdsourcing services to conduct studies faster, this might make crowdsourced self-report data fundamentally unreliable, as these responses would be hard to distinguish from real data. I thank you for your attention.